Let me start in a simple way, because the deepest ideas in physics usually hide inside the simplest questions. Imagine you walk into your kitchen one morning and find a cup on the table. The cup is whole. It has a nice shape. Now imagine you come back later and the cup is shattered on the floor, broken into 1,000 pieces. That feels normal. We've all seen it happen. But if you walked in one day and saw 1,000 shards of ceramic suddenly leap up from the floor and assemble themselves neatly into a perfect cup, you would stop breathing for a second. You would think you were dreaming. You would call someone. You would check the room for hidden wires. Why is that? What exactly makes one situation ordinary and the other almost impossible? Nothing in the basic laws of motion forbids the pieces from flying together. The atoms obey the same forces in both cases. Yet one direction happens all the time, and the other never does. This difference is not about cups. It is about the universe. Physics has many laws that are neat, symmetric, and elegant. If you write them down, most of them do not care whether time runs forward or backward. If you film two planets orbiting each other and play the film in reverse, the motion still looks perfectly legal. The equations don't complain, but real life does complain. Real life has a clear direction. Eggs break, but they do not unbreak. People age, but they do not grow younger. Smoke spreads out in a room, but it never politely gathers itself back into the cigarette. So the real mystery is not motion or force. The real mystery is why things run down. This question bothered physicists for a long time. It bothered engineers even more, because engines always waste energy. No matter how clever you are, no machine ever turns all its fuel into useful work. Some of it always leaks away as heat. That leak is not an accident. It is a law. And like all good laws of physics, it applies everywhere, whether you like it or not. To understand this law, we need a strange quantity with an even stranger name: entropy. Now, when people hear that word, they often imagine chaos, mess, or disorder. That picture is not wrong, but it is not precise enough to be helpful. Entropy is not about mess, in a moral sense. It is about counting. Suppose I give you a brand new deck of cards, neatly ordered by suit and number. That deck looks special. Now shuffle it well. The deck now looks ordinary. Here's the key point. There is only one neat order, but there are an enormous number of shuffled orders. If you shuffle the cards randomly, you are almost guaranteed to land in one of the messy arrangements. Not because the universe prefers mess, but because there are vastly more ways to be messy than to be neat. Entropy is a way of measuring how many microscopic arrangements correspond to what you see on the outside. A low entropy state is special and rare. A high entropy state is common and typical. Nature does not push systems toward disorder out of spite. Systems simply drift toward what is most likely. This idea becomes clearer if we think about atoms. Everything around you, air, water, your body, the stars, is made of tiny particles bouncing around according to simple rules. You do not see the particles. You see averages. When gas fills a room, it is not because each molecule wants to explore. It is because there are vastly more ways for the molecules to be spread out than to stay clumped in one corner. Spread out states win the numbers game. Now here is where probability quietly takes control of the universe. The laws of motion tell particles what they are allowed to do. Entropy tells us what they are overwhelmingly likely to do. The second law of thermodynamics says that in an isolated system, entropy tends to increase. Not always, not instantly, but almost certainly over time. The word tends is important. This is not a commandment. It is a statistical truth. If you flip one coin, you might get heads. If you flip 1,000,000 coins, you will almost certainly get very close to half heads and half tails. Entropy works the same way. In small systems, weird things can happen. In large systems like cups, oceans, planets, and galaxies, the numbers are so huge that reversals become fantastically unlikely. This brings us to time. Why does time feel like it flows in one direction? Why do we remember the past but not the future? The answer is not hidden in clocks or brains. It is hidden in entropy. The past is the direction of lower entropy. The future is the direction of higher entropy. Memory itself depends on this. To remember something, you must create records, and records increase entropy. So a universe without increasing entropy could not even remember itself. This is a strange idea. It means the arrow of time is not built into the fundamental equations. It emerges from statistics. Time's direction is a matter of overwhelming odds. Now let's talk about heat, because heat is entropy in disguise. Heat is energy spread out among many particles in many small motions. When energy is concentrated, say in a moving piston or a spinning wheel, You can use it to do work. When that same energy is spread thinly as random motion, it becomes almost useless. The energy still exists, it has not vanished, but it has lost its ability to organize anything. This is why engines cannot be perfectly efficient. To extract useful work, you need a difference. Hot and cold, high and low. As the engine runs, those differences shrink. Heat flows from hot to cold. Entropy increases. Eventually everything evens out, and the engine stops being useful. You can think of entropy as the price the universe charges for doing anything interesting. At this point, you might wonder whether intelligence can cheat. After all, living things create order all the time. Plants grow, cities rise. Life seems to fight decay. But this is only half the story. Life creates local order by increasing disorder elsewhere. A growing plant releases heat. A city burns fuel. A brain thinking hard warms the room. Life does not violate the second law. It depends on it. To see why, imagine the universe as a giant accounting system. You are allowed to decrease entropy in one place, but you must pay for it by increasing entropy somewhere else, and the total bill always goes up. There are no refunds. Now we can begin to zoom out. So far we have talked about cups, cards, engines, and rooms full of air. But the laws we have used do not stop at the edge of your kitchen. They apply to stars. They apply to galaxies. They apply to the universe itself. Stars shine because they are hot in a cold universe. They burn fuel, converting concentrated nuclear energy into spread out radiation. Every second, stars increase the entropy of the universe. That is not a flaw in stars. That is what they are for. But fuel is finite. Stars cannot shine forever. When stars burn out, galaxies grow dim. Motion slows. Black holes evaporate extremely slowly. Over immense stretches of time. Time so long that writing them down feels absurd. The universe drifts toward a state where energy is spread as evenly as possible. No gradients, no differences, no engines, no life. This final state is not dramatic. There is no explosion, no curtain falling, just quiet. Energy still exists, but it cannot do anything useful. This is sometimes called thermal equilibrium. Everything has the same temperature. Nothing happens. What makes this unsettling is not that it is violent, it is that it is boring. And here is the part that people find hardest to accept. Nothing has gone wrong. This outcome is not caused by a mistake, a collapse, or a cosmic accident. It follows naturally from the same statistical law that explains why coffee cools down and cups shatter. The universe is simply doing what is most likely. Now let me say something important. Physics does not tell you how to feel about this. It does not say the universe is cruel or pointless. It only tells you how things behave. Meaning is not removed by understanding. If anything, understanding sharpens it. Knowing that order is rare makes it precious. Knowing that time is limited gives weight to every moment. There is a temptation to look for loopholes. People ask whether the universe might reverse, recycle, or start over. These are interesting questions, and physics has not finished answering them. But so far, every serious attempt to escape the increase of entropy runs into the same wall. Probability is relentless. You can delay it, you can shape it locally, you cannot eliminate it. The lesson here is not despair. The lesson is honesty. Nature does not promise permanence. It offers patterns, laws, and an astonishing ability for simple rules to create complex, beautiful things for a while. That for a while is not an insult. It is a condition. Music exists only because notes begin and end. Stories matter because they have a last page. Life is meaningful because it is not infinite. So when we talk about entropy and the long-term fate of everything, we are not talking about doom in a dramatic sense. We are talking about the quiet truth that change has a direction, that usefulness fades, and that the universe is not obligated to preserve our favorite arrangements. What it does preserve remarkably well are its rules. And those rules are simple enough to explain with cups, cards, and coins, yet powerful enough to shape the destiny of stars. If that feels a little uncomfortable, good. Physics is not here to comfort us. It is here to tell us what the universe does, whether or not we were hoping for a different answer. Let's continue by pushing the same ideas a little farther than feels comfortable, because that is usually where physics becomes interesting. Up to now, we have talked about entropy in everyday systems, and hinted that the same rules apply to stars and galaxies. Now we will follow that idea all the way out, to scales so large and times so long, that ordinary intuition stops being useful. One of the hardest habits to break is the idea that the universe is somehow different from everything inside it. We imagine special rules for the cosmos, as if it were exempt from the laws that govern coffee cups and engines. But physics does not work that way. The universe is not outside the system, it is the system. And that means the same accounting rules apply. To see why this matters, think again about how change works. In mathematics, especially in calculus, we often care less about exact values than about trend. We ask, is something increasing, decreasing, or staying the same? We look at slopes rather than points. Entropy is exactly this kind of quantity. It is not important to know its precise number. What matters is its direction. When we say entropy increases, we do not mean it jumps suddenly. It creeps, it flows, it approaches limits. In calculus, we talk about limits all the time. A curve can approach a line without ever touching it. A process can slow down without ever stopping completely. The universe behaves like that. It is always on the way somewhere, even if it never quite arrives. Now imagine the universe shortly after it began. It was hot, dense, and remarkably uniform. That uniformity might sound like high entropy, but here is a subtle point. Gravity changes the rule. When gravity is strong, a smooth distribution of matter is actually low entropy. There are many more ways for matter to clump than to stay perfectly even. So, as the universe expanded, gravity pulled matter into stars and galaxies, increasing entropy while also creating structure. This is why the universe can become more complex while still obeying the second law. Complexity is not the opposite of entropy. In many cases, complexity is how entropy increases. Stars form, burn, explode, and spread heavier elements. Planets form, chemistry gets richer, life becomes possible. All of this happens while the total entropy keeps rising. But complexity is temporary. It exists in the middle of the process, not at the end. In calculus terms, it lives in the transient behavior, not in the final state. The final state is simpler, not because simplicity is favored, but because nothing is left to change. To understand why the universe cannot simply keep recycling itself forever, it helps to think about energy gradients. Useful processes depend on differences, hot and cold, dense and sparse, high and low. As long as there are gradients, things can happen. Calculus tells us that change depends on differences over distance or time. When the differences vanish, the derivatives go to zero. Nothing evolves. The universe started with enormous gradients. Stars were hot compared to space. Matter was dense in some places and thin in others. Over time, those differences shrink. Heat leaks into cold space. Motion slows. Structures decay. This does not happen because the universe is trying to rest. It happens because there are more ways to be even than uneven. You might ask whether expansion saves us. After all, space is getting bigger. Doesn't that create new room for gradients? Expansion does spread energy out further, but that actually helps entropy increase. As space grows, energy becomes more dilute and less useful. Expansion is not a reset button. It is part of the same story. At this point, people often hope that quantum mechanics will rescue us. Quantum physics is strange, subtle, and full of surprises. Surely there must be a loophole there. Quantum effects do matter, especially on very small scales and very long time. Black holes, for example, slowly lose energy through quantum processes. But here is the disappointment. Those processes also increase entropy. They do not reverse it. They just finish the job more thoroughly. Over unimaginably long times, black holes evaporate, particles decay. Even protons may not last forever. What remains is thin radiation, spread almost perfectly evenly. No clumps, no engines, no chemistry. This is not because physics breaks down. It is because physics keeps working. Now let me be careful. Physics is not complete. We do not know everything. Anyone who tells you otherwise is selling something. There may be surprises ahead. But good scientific thinking does not rely on hope. It relies on what we can calculate and test. And every calculation we trust points in the same direction. Entropy wins. This is where advanced mathematics quietly supports the conclusion. When you model large systems with many degrees of freedom, the most probable states dominate behavior. As systems grow larger, fluctuations become negligible. In the limit of enormous time and size, probability becomes destiny. Not absolute destiny, but practical destiny, the kind that matters. People sometimes imagine intelligence as a kind of cosmic rebel, able to outsmart nature indefinitely. But intelligence is a physical process. It requires energy, it produces waste, it runs on gradient. A thinking machine, no matter how advanced,
still pays the entropy bill. You can postpone the end by being clever. You cannot cancel it. This does not make intelligence pointless. It makes it rare, and rarity is exactly what entropy predicts. Now why should we care about this at all? After all, these timescales are absurdly long, longer than stars, longer than galaxies, longer than anything we will ever see. Why think about it? The answer is that understanding the end helps us understand the present. When you realize that order is temporary, you stop taking it for granted. When you see that the universe allows structure only briefly, you begin to appreciate how extraordinary it is that we exist during such a brief window. Physics does not rob the world of wonder. It explains why wonder is possible at all. There is another important lesson hidden here. Many people confuse science with nihilism. They think that if the universe does not guarantee meaning, then meaning does not exist. That is a mistake. Physics describes what happens, not what matters. Meaning is something we create inside the constraints of reality, not something handed down by equations. In fact, constraints are what make creation meaningful. A game with no rules is boring. A universe with no limits would have no stories. The fact that things end is not a flaw. It is a condition for significance. So when we say that the universe drifts toward a quiet, featureless state, we are not saying that everything is pointless now. We are saying that now is special precisely because it is not that state. Let me end with a thought that often gets overlooked. The same laws that predict the fading of stars also predict their birth. The same statistics that guarantee decay also allow rare pockets of order. We live in one of those pockets. We are the kind of thing that can only exist far from equilibrium. That is not an accident. It is a consequence. The universe does not care about us in the sense of having intentions, but it does allow us briefly, and in that brief allowance, we get curiosity, understanding, and the strange ability to look at the universe and ask what will happen to it long after we are gone. That ability is not defined. It is participation. We are part of the same process we study. Our thoughts are tiny rearrangements of matter and energy, paid for by entropy like everything else. And that, oddly enough, is comforting. It means we are not spectators watching a machine wind down. We are gears inside it, turning for a while, making patterns that exist only because the universe is not yet finished. Physics does not promise eternity. It offers something better, a clear picture of how things work, and the freedom to find meaning inside that picture, without illusion. If the universe must one day grow quiet, that does not make the present silent. It makes it sing.